All right, Emitle, we are continuing on from our last session on this question 10 on the photoelectric effect. So we had this very last section, 10.4 left. They giving us a few options here from increase, decrease, or no effect when we answer these questions. And it is always important when we answer these questions to listen to those instructions. So let's have a look. 10.4, the experiment is now repeated. The experiment is now repeated for cathode M. When we look at the graph, this is cathode M up here, using a light of frequency fx, all right, but of higher intensity. How will each of the following be affected? Now, it's important for us to first just remember what is intensity of light. Now, remember, light is coming with packets of photons that are incident on a metal, and a higher intensity doesn't necessarily mean more frequent photons. It just means that more photons will be hitting it at every single time. And so the frequency of light stays the same at how often that energy comes in. It is just more photons that are coming in. Right, so how does that change everything? What does it do to the y-intercept of this graph? This y-intercept is the frequency, and that still stays the same. The frequency has not changed, and so there is no effect on the first one. Let's continue. 10.4.2. What does it do to the number of photoelectrons emitted per unit time? Well, if more photons are coming in at every interval, then more photoelectrons will be emitted. And so the photoelectrons emitted increases as more photons are hitting the metal. And then lastly here, 10.4.3, the maximum number of the maximum kinetic energy of the emitted photoelectrons. Well, for each photon that hits a photoelectron, it will have the same frequency, therefore the same amount of energy for the incoming light. If the same amount of energy is still coming in for each photon, that same amount of energy is transferred to each electron. And so therefore, there will be no increase in the maximum kinetic energy. The effect on kinetic energy will be no effect. All right. And that really concludes coming to an end of what is most standard for almost all the old exam papers. I do want us to take a pause in just a moment here and note that if we make sure that we go through all the content that we have done and make sure that all the work is done, we might notice that there are some areas that are missing. Specifically, I want to mention the light spectra, emission and absorption spectra section of the work. It was following very closely after the photoelectric effect, and it was when light that passes through hot gas, warm gas versus cold gas has two different effects in how that gas absorbs and then again emits light. So we just need to make sure that we are making sure to study all the work and not just go through all the exam papers. So please remember to, in your preparation, make sure to go through, yes, all the exam papers, but also just to revise all the work that has been covered. I'd like to point out that if you go through all the exam papers, you would have to go back to 2017, in fact, to find a question on atomic absorption and atomic emission spectra, which really is quite far back, quite a while back. So I think what would be good for us in this section and this session and the next, so that means this week's session and then the following week's session, is I would very much like to go back to 2017 paper. It is still in the content for CAPS, and so you are still expected to be able to do those questions. However, it is far enough back that the questions differ a little bit from um, how they were asked in the past 2 years. which I think is beneficial because they might just draw on those few years back. As they have been repeating the same questions recently, yes, we do practice them, but we also get exposure to different types of questions. And going back a few years to when somebody else, another examiner, was setting up question papers, then we can have a look and learn from them. So, starting off in this question 11, this was from paper 1 on 2017 for November NSC exams. Okay, so please make sure I have also uploaded all the question papers from 2021 all the way through to 2017 on the classroom on Moodle for you. So please just make sure to go have a look, as well as I've uploaded the annual teaching plan. It's called the ATP. It is not something generally used by learners. It's actually more used by teachers, but this could be beneficial for you to just double check the work that has been covered and the work that you should be able to cover. All right. So please just go have a look at that. But for now, let us work on this question 11 from 2017. So this question starts off, well, with a diffraction grating, and this is going to be spectrum and spectrum. This is light absorption and light emission spectra. A teacher in a science class, this is 11.1. A teacher in a science class explains how different types of spectra are obtained. The teacher uses the simplified diagrams below for the explanation. You've got hot gas and light flowing through it that shines through a diffraction grating to create spectrum Y, and then hot that hot glowing bulb, that light shining through cold gas, and then through a diffraction grating to create spectrum Z. Name the type of spectrum of 11.1.1? Well, let's have a look. 11.1.1 Y. In spectrum Y, we have light going through hot gas, and we will see the emission spectrum. Okay, that's, remember, just going to be for studying. The emission spectrum will always be seen when light goes through hot gas. And so that's going to be the emission spectrum. 11.1.2, that is the only other spectrum that we know, and that is going to be when light goes through cold gas, we see the absorption spectrum. Absorption spectrum, excuse me. Right, and so yes, an easy 1 mark and 1 mark. That is not too much, but we can see this is not the only thing that we see on absorption and emission spectra. Now, the second question. In an excited atom, electrons can jump from a lower energy level to higher energy levels. They can also drop down from higher energy levels to lower energy levels. The diagram below, not drawn to scale, shows some of the transitions for electrons in an excited atom. So we see some movement. These arrows downwards are indicating what electrons are doing. They're going from an energy level 4 to an energy level 2, and also maybe an energy level 3 to energy level 2, where this is the amount of energy, and it goes to a lower amount of energy and an even lower amount of energy. So 11.2.1. Do the transitions indicated in the diagram lead to absorption or emission spectra? Just a reminder, the absorption spectra is when light is absorbed by an atom. And the emission spectra is when light is emitted. And when we see that these electrons are going from a higher energy level to a lower energy level, that means that they're losing energy. And that energy goes somewhere, and that energy is emitted in the form of light. And so for this, when we see electrons go from higher energy to lower energy, we see that we have an emission spectra. Right. Emission spectra. Continuing on, 11.2.2. Now they're asking us to calculate the frequency of the photon produced when an electron is in an excited atom like this, makes a transition from E4 to E2. Right, so going from this energy level to this energy level, as shown in the diagram. Now we'd have to note that Well, if it goes from this energy level to that energy level, it loses that much energy. So let's see what the energy released would be. So the energy that that electron is emitting would be E4 minus E2. And we have E4 being 2,044 times 10 to the power of negative 18. And then we subtract 1,635 times 10 to the power of negative 18. And that should give us, here we have calculated work at hand. That should give us a 4,09 rounded times 10 to the power of negative 19 joules. Now that is the energy that is lost by this electron going from the high energy level to the low energy level. That is the energy that is emitted, and it is emitted in the form of light. Now I know light energy has this formula, and it is so coincidental that they're asking for the frequency of the photon produced. The frequency of the photon produced when I know what the energy of that light is, and Planck's constant, of course, we have. So the energy in this case is going to be 4,09 times 10 to the power of 19, negative 19. I know Planck's constant is 6,63 times 10 to the power of negative 34 multiplied by frequency. Solve for frequency, and the calculator will do the rest. That's going to be 4,09 times 10 to the power of negative 19 divided by Planck's constant. Okay, and a quick calculator will do that for us. I've done it slightly earlier just to save some time. That's going to be 14 hertz. 10 to the power of 6,17 times 10 to the power of 14 hertz. All right. Nice, easy 4-mark question. Let's have a look. Let's continue. 11.2.3. What is going on? They tell us the threshold frequency of a metal, Q, is 4.4 times 10 to the power of 14 hertz. And now we're going back into the previous content that we were working with, which is the photoelectric effect. Now another metal R, here they're telling us calculate the kinetic energy of the most energetic electron ejected, that is the max kinetic energy, when the photon produced in 11.2.2, that is this photon, right, is incident on the metal of surface Q. Calculate the kinetic energy, the maximum kinetic energy. I know that the energy that is incident on metal will be equal to the work function of a metal added to the kinetic energy, the maximum kinetic energy. Now that really helps us because we can expand this. We know what the energy is of the photon. They're asking for the max kinetic energy, and the work function of the metal is simply Planck's constant multiplied by the threshold frequency. All right. And so we can simplify this, or we can substitute and simplify. The energy that we calculated this photon to, or this electron to have, would be 0.9 times 10 to the power of negative 19. The work, Planck's constant, 6,63 times 10 to the power of negative 34. The work threshold frequency, at least, is 4,4 times 10 to the power of 14. And then plus the kinetic energy, running out of space ever so slightly. Let's move it up just a teensy bit. And this is really just simplifying and solving for the max kinetic energy. So that would be the energy of the photon, 4,09 times 10 to the power of negative 19. And then we subtract Planck's constant multiplied by the threshold frequency. Okay, and again, just for some time, this would be our answer. Okay, and just a reminder of the units of energy, whether it is energy of a photon or kinetic energy, it is always joules. Energy is measured in joules. Right, let's have a look. Next question, 11.2.4. Another metal R has a threshold frequency that is greater than the previous metal. Okay, there's a higher threshold frequency. That means we need more energy to emit an electron. Now, will the photon produced in 11.2.2 be able to eject an electrons from the surface of the metal R? Write down only yes or no and give a reason for your answer. Okay, and we can have a look there. I expect, let's have a look, the threshold frequency, I believe, will be greater than the frequency of the photon. Frequency of the photon is 6,17. This is the frequency of that light that is incoming. And I see the threshold frequency is 7,5 times 10 to the power of 14. And so this frequency is insufficient. It is not high enough. And so the answer will be no. Okay, the photon produced will not be able to eject electrons. And the reason is that the threshold frequency is higher than the frequency of the photon. And see again immediately how this question starts asking us in a different manner from the previous session. So if you're watching these two sessions from last week and this week directly after each other, it'll be really beneficial just for your getting an idea of what different examiners and how they could set up different questions. Still the same content, but worded and asked differently. On this, while we're on 2017, I think it could be good to just, for these next two sessions, work on specific questions. And so let's have a look on the specific questions that I want us to look at. I've identified a few that are important for us just to revise. I'd like us to start off on maybe one that is slightly easier, but what I'm specifically after is this last question 3.4, which we will get to, drawing a velocity versus time graph. Very standard, and we need to know them. So as we start with question 3, we need to interpret what is going on. This is a vertical projectile motion question. Let's have a look. Stone A is projected vertically upwards at a speed of 12 meters per second from a height h above the ground, as indicated in this graph. Ignore the effects of air resistance. Oh, thank goodness we ignore the effects of air resistance. 3.1. Calculate the time taken for stone A to reach its maximum height. And this is very easy for us to remind ourselves. It's a good practice for us to remind ourselves what we need to do in the process that we use in answering vertical projectile motion questions. Remember, first step is write down the values that we have, the knowns and the unknowns. And so we have, let us, before then even just state which direction we want to be positive. Let's choose upwards to be positive and stick with that throughout the entire question. As long as we're consistent, we make less mistakes. So let's have a look what we have. We've got some initial velocity. Initial velocity is 12 meters per second upwards. We have the final velocity when it reaches its maximum height. Balls moves up, the stone moves up, and then at its maximum height, there is no velocity. And so it's got 0 velocity, meters per second velocity, that's maximum height. We are asking for the maximum height, and the height would be, well, let's say x, or let's say y. I'll change it y. That is what we don't have. Is there any other value that we want? Calculate the time taken for stone to reach its maximum height. No, this is not what we're looking for, in fact. This is not even taking part in our equation. We always have acceleration, right? Acceleration is negative 9.8 meters per second squared. What the question is asking for is time, change in time. And so the question becomes very quickly quite easy if we But which formula we need to use is the only formula that includes those four values with one unknown, which is that of time. And so when we do our substitution, we make sure that we're choosing direction to be positive. Final velocity will be 0, initial velocity positive 12. Our acceleration is negative 9.8 because that is gravity is working downwards. And then our change in time is the unknown. And 12 divided by negative 12 divided by negative 9.8 give us a change in time of 1.22 seconds. Easy 3 marks. Formula, substitution, answer. 3.2. Now let's see what happened. At the same instant that stone A is projected upwards, stone B is thrown vertically downwards from the same height at an unknown speed, and so it does not start from rest. Refer to the diagram below. When stone A reaches its maximum height, that means after 1.22 seconds, the speed of stone B is 3 times its initial in the unknown speed, 3v. 3.2, calculate the speed v with which stone B is thrown downwards. Now let's have a look. We're focusing on stone B. Do we know the change in time that they were talking about? Yes, it was a 1.22 seconds. The same time that stone A reaches its maximum height. Stone B has a velocity of 3b. Okay, important one. Now let's have a look. Do we have initial velocity? They said initial velocity. We don't necessarily have the value, but we know it is a value of v. And our final velocity is a value of 3v. Now, bearing in mind that we still have upwards as positive, we will need to say that it is negative v and negative 3v if we are keeping upwards as positive. Do we know the acceleration? Yes, of course we know the acceleration. It would be negative 9.8 meters per second squared. Do we have a formula that we can use that includes these four values? Yes, we do. We have the same formula as above. Vf is equal to Vi plus acceleration over change in multiplied by change in time. Our V final is minus 3v. Our V initial is negative v. Our acceleration negative 9.8. And our change in time, a value that is 1.22. Let us do some simplification here. I'll show you the simplification just very short. I take this v across and I would add it. I would be left with negative 2v and negative 9.8, 1.22. And to simplify, you'd divide both sides with negative 2 to find this value of v. And this value of v would give us 6 meters per second rounded off, it seems. And that is the answer to the question. Calculate the speed v with which stone B is thrown downwards. Please note that this is a positive value, but we just need to bear in mind they're asking for that value of positive v. I have already taken into account that negative, so that this answer being positive does not necessarily indicate that it is an upward velocity. I am simply calculating this value of v, which in their sense is, in their equation, is just a magnitude, okay, with no direction. So let's continue. 3.3, calculate the height of h. And so how do we do that? Now, question becomes, excuse me, what are the values that are known and what are the values that are unknown? Keeping upwards as positive. Now, do we have what it takes to tell us, do they give us any unknown? Oh, they do tell us. At the instant stone A passes its initial position, okay, so stone A has gone up and then come back down. At the instant stone A passes its initial position, on its way down, stone B hits the ground. Ah, wonderful. All right, so let's have a look at the stone A. It is being thrown up. Let's do this in another color, a different color in green, and we'll do it in a large one. So stone A goes up to its maximum point, and it took 1,22 seconds to reach that point, and it comes back down after its initial position. Once it reaches that initial position again, that's the point at which stone B hits the ground. How long did that take, though, for stone A to do this whole loop? Now there is a little trick that we can use, although it's not a trick, you might have even learned it in class, depending on your teacher, is that for any object, if we are ignoring air resistance, the time that it would take to go from point A to its highest point, and then from that highest point back down, that time interval for that first section will be the same as the time interval for that second section. Right. That is very, very helpful. Because if I know that it took stone A 1,22 seconds to reach the top, it would also take 1,22 seconds to come back down. That means that our change in time in this case is possible for us to calculate. The change in time for stone A to go up and then back down to its original position is going to be twice 1,22 seconds. That's a little trick that we can use. You can do the calculation if you'd like for it again to find out what it would be to get back down, although that is a bit much when we can make that assumption. That is a safe assumption. So let's continue. We've got the change in time. They're asking for this height then that B would drop, because that is the same time that B is dropping from. I have the initial velocity that B is thrown at. The initial velocity that B is thrown at would be negative 6 meters per second. Remember, that is downwards after all, should be negative. I have the acceleration, it's negative 9,8. I have, what I'm looking for is my change in height, that is delta y. Do we have an equation that includes these four variables? Let's have a look. Change in time, acceleration, initial velocity, and change in y. I believe there is one, and I really do hope you have your formula sheet with you for paper 1. Remember, I asked you to always have it with you. This formula should work. Plus a half acceleration times squared, change in time squared. And we're looking for that change in y. That's wonderful. That's simple substitution from here on out, making sure we choose the right values. And so negative 6 multiplied by time, which is 2,44, plus a half, and then acceleration again, negative 9,8 multiplied by change in time, all squared. All right, and that should get us somewhere around 43. 43, it seems like 43,9. I'm getting different values here, or at least mine is differing from the memo, it seems, but I think the memo is using a different value. So let's go with the, should be around there. They are allowing some range. There is some range allowance here. So if you get somewhere very close to this value, you should have full marks. And again, very nice quick one. For 3 marks, formula substitution answer. Please bear in mind that for these questions, when there's only 3 or 4 marks, there is very little work that goes into it. And so let's just add the mark allocation here. Formula substitution answer. That first question was also formula substitution answer. In this one, we would have formula, and then because we are substituting a number of different values here, these two would be awarded 1 mark, and those would be awarded 1 mark. And so 2 marks for substitution here, and then 1 mark for the final answer. So it was 4 marks in total. Now, lastly, let's have a look at sketching this velocity versus time graphs. So, now this is not something that we've seen in paper 2021, and so please just be reminded that these velocity versus time graphs are important and are almost always asked. We need a good understanding of what the question is, what is happening in the question. So make sure that you read and understand what the situation is about. Let's zoom in slightly. Question says, sketch the velocity over time graphs for the complete motions of stones A as well as B on the same set of axes. Label your graphs for stones A and B clearly. Now, let's just add our labels for this graph. On the y-axis, we have velocity. Right, this is velocity over time graph, and for that reason, we would have to have velocity on the y-axis. Okay, so the velocity on the y, oops, let's just do that. We have the velocity over there, and we have time over here. All right. Now, a reminder for us to find what these values were. What was their initial velocity? And I'm still going to be working with upwards as positive. And so the stone A started with some initial velocity. Remember, I wrote it down at the start. My very first question. So let's work with stone A first. Stone A had some positive upward velocity. And so we'll add that. At 12, stone A had some positive upward velocity, and as time went on, it reached its maximum height where it had a zero velocity. And so it had a positive velocity, and then it decreased to have a zero velocity. And then, instead of having an upward velocity, ball A turned down and it had a negative velocity, because remember, my upwards is positive. And so as the ball goes down, its velocity becomes more and more negative. And so the ball's A velocity becomes more and more negative. Okay. Now we don't necessarily calculate that final value with which it struck the ground, but that's all right. This can be stone A. At which time did stone A reach its maximum height? At which time did it have a zero velocity? Well, the time was 1,22 seconds. That's important to note. Let's have a look then at stone B. Stone B, it had started with some initial downwards velocity, and so it had some initial negative velocity, which we calculated was -6. And then it continued speeding up downwards. Its velocity increased as it went down, so the velocity became more and more negative until some point that it hit the ground, which we can also give as a value, which was 2,44. And we indicate that. Make sure when you're drawing these velocity versus time graphs that you're giving the units. It would be meters per second, and time is measured in seconds. Also indicate all the values on your y and x axes, as I've done here, and also label the graphs if there are more than one. And that's going to be it for a pretty standard vertical projectile motion question, including this addition of the velocity over time graph. And you can see how really easy they can become if you make sure that you write down the values of the knowns and the unknowns. Okay, continuing on in the same question paper from paper 1 in 2017. Moving on to question 5, the work energy theorem. And the reason I'm bringing this up again is because I mentioned on the question that you've answered on the test that you wrote for me, Amicle, was that we could work on how we answer these questions. You got yours right, but by using a different method from what is considered standard. And so I was really quite impressed, and I encouraged you to continue thinking in that way, to problem solve, even when you don't know exactly what to do. You got there and your logic followed. But I do want us, and I would like you to practice making sure that you use the same, or the work energy theorem in these questions. Start getting used to calculating work rather than focusing too much on forces, the net forces. Start thinking in terms of net work. Okay. So, first question, 5.1, state the work energy theorem in words. And once again, I really hope you're going to the exam guidelines. The exam guideline says that the work energy theorem, and I'm going to read it off of the exam guidelines, is the network done on an object is equal to the change in the object's kinetic energy. Object's kinetic, oops, kinetic energy. A very short and quick one, but an easy 2 marks. So please make sure you're going through and using the exam guidelines there. So 5.2, next question. Well, hold on. Let's understand what's going on first. In the diagram below, a 4 kilogram block is lying on a rough horizontal surface. It is connected to a 6 kilogram block connected by a light inextensible string passing over a light frictionless pulley. Initially, the blocks are held at rest. Okay, so initially, there is 0 initial velocity. Right, let's have a look. This box is then, when the blocks are released, the 6 kilogram block falls through a vertical distance of 1,6 meters. Okay, so there is definitely some work being done because there is distance being covered. Let's have a look. 5.2, draw a labeled free body diagram of the 6 kilogram block. Right, 6 kilogram block has 2 forces acting on it, I believe. It's got one acting upwards, one acting downwards. The one acting upwards is the tension in the string. The one acting downwards is the force of gravity or the weight. Please note that there are a very few number of labels that we can use to indicate these forces. Okay. Tension works well, tension is allowed. They also allow the force of tension, like F subscript T. They also allow you to write out tension. But as I've mentioned to you before, we will stick with capital T. And for weight, weight is allowed. We also allow the force of gravity or the force of weight, or mg is also sometimes allowed. However, you can say the force of Earth on the block. You can say also the gravitational force. However, I'd very much like us to stick to only these 2 options for both of them, just for surety, to make sure we're not losing any unnecessary marks. Okay, 5.3. Calculate the work done by the gravitational force on the 6 kilogram block. Well, the gravitational force we know is mass times gravitational acceleration. And, well, the work done by gravity or the work done by the weight is simply going to be, well, the weight multiplied by distance covered multiplied by cosine of the angle between the force and the displacement. And so mg, and this should actually be not cosine x, but cosine y in this case, because this is vertical movement. Although there will be some leniency and you don't need to be too strict on that. Mass times gravity, this is 6 multiplied by 9,8 multiplied by displacement, which is 1,6 multiplied by cosine of 0. That means just 1. A quick calculation there will tell us that the work done here by weight is 94.08 joules. That is very nice. It's very important for us to know that in this case, the blocks are released. 6 kilogram block falls through a vertical distance of 1,6 meters. That's nice for us to know because we can talk about the energy that is done or the work that is done to this block. Okay, let's continue. 5.4. There we go. Let's see how much time we have left, just for a second. All right, now we still have enough time. Okay, 15 minutes. 5.4. The coefficient of friction between the 4 kilogram block and the horizontal surface is 0.4. Ignore the effects of air resistance. Okay, wonderful. Let's have a look. Use energy principles to calculate the speed of the 6 kilogram block when it falls through 1.6 meters while still attached to the 4 kilogram block. Now, use energy principles to calculate the speed when it falls through 1.6 meters and using energy principles. I think I remember telling you what energy principles means for us. Now, energy principles, that is the work energy theorem. That is W net is equal to change in kinetic energy. So, change in kinetic energy, how is that going to help us? Well, I know the change in kinetic energy does talk about speed. The initial speed that we have is 0, and that final speed, the speed of the 6 kilogram block when it falls to that 1.6 meters. And so we can expand that. We can also talk about the W net, the net work that is done. The net work that is done on that 4 kilogram block, well, the work that is done by the 6 kilogram block is going to be equal to the work that is done by gravity on that 6 kilogram block because there's only these two forces acting on it. Okay, they are in equilibrium. So let's have a look then. What happens when we expand the net work? The net work is going to be the work of friction. That is a force that is acting on the 4 kilogram block. There is also the work done by gravity. There is also the work done by the normal force. And this will all be equal to, well, the change in kinetic energy. Let's expand that as well. You've got one very large equation. You've got a half m final velocity squared minus initial velocity squared. All right, I've got a whole very many values, and we will find that we can calculate them all right here. So let's have a look. We have the work done by friction. Hold on. That would be the coefficient of friction, which they give us. The coefficient of friction is given is 0.4. The work done by friction is the force of friction. So that's mu times normal multiplied by the distance covered multiplied by cosine of the angle between the force and the displacement. And then we add the work done by gravity, but that we have. So I'm going to leave that. And then the work done by the normal. I will talk about that in a second. All right. A half m, and we just leave these values. We're just expanding to find all the values so we can substitute into each one. So let's have a look here. The mu is 0.4. The normal is the mass times gravitational acceleration, 4 times 9.8. The displacement is 1.6. If 6 kilogram block moves 1.6, then 4 kilogram block will also move 1.6 meters because they're passing over a light inextensible string, or they're attached with one by one. And then the direction is going to be cosine of friction. Friction is acting in that direction. Movement is in this direction. That means cosine of 180. All right. Therefore, now we can substitute the rest. The force of gravity was, or the work of gravity was this, and the work done by the normal force is an absolute 0. Beautiful. Let's have a look then. We find that on the right hand side we have these unknowns. Mass is 4. There's a lot of values here that we know and don't know. Let's have a look. We have final velocity. Final velocity is unknown. The initial velocity is 0. Okay. And solving for final velocity here, again, I'm looking at the memo just for the sake of time. I'd have us rather just do this, but remember, please make sure that you have to practice your calculator work. All right, so let's try this one another time, maybe when we go through or when you go through your own question papers. Okay, so let's have a look at the, oh, that was the very last question. Wonderful. Okay, marking allocation. Let's have a look. Got 2 marks for the definition, 2 marks here, one for each value, both 2 and 2. The third question, 5.3, was 3 marks. That would be formula substitution and the answer. 5 marks here finally would be for the formula. One of these, any one of these should be fine. And then we have here 1 mark for calculating the work done by friction. If you would do that separately, you would only still get 1 mark for that. And then you have, excuse me, 1 mark for the substitution of the others, 1 mark for the substitution of the frictional, of the kinetic energy on the right-hand side values, 1, 2, 3, 4, and then, oh, there we go, 1 mark for the final answer. Okay, so now that is the work energy theorem question. Please note that you need to make sure you're practicing these. Okay, let's see if we have some time maybe for another question. I believe we should almost be up. But I think that will be all that we have time for today.